Hello everyone, and welcome to class number 31 of Physics 218. So last time we talked about the finite square well potential energy. Today we're going to build on what we learned about that and learn about making qualitative sketches of bound state energy eigenfunctions. Now why do we want to do this? So if you watch the bonus video for the last class, you'll realize that even in the relatively simple case of a finite square well, nice solutions of the time-independent Schrödinger equation are hard to come by. For most potential energies, except for a handful of sort of special cases, you do have to resort to numerical solutions. And being able to reason about what the bound state energy eigenfunctions might look like helps to provide a plausibility check on the output of any such code. And moreover, thinking about qualitative sketching is a really nice way to build intuition about 1D quantum mechanics. So we'll begin today by talking about some of the properties of bound state energy eigenfunctions, and we'll make a lot of reference to what we learned about the finite square well. And one more thing, so I prepared a handout summarizing the principles I'm going to talk about for doing these sketches. And if you want, I'd encourage you to refer to it now, and I'll highlight in this presentation some of the more important points. So the first thing that I want to talk about is the behavior in classically allowed regions. So that's where the energy is larger than the potential energy. So I've sketched this for a finite square well here, using the pretty typical representation where we plot the potential energy as a function of x and draw the system energy, or the energy eigenvalue, as a constant horizontal line, because we assume that energy stays constant. For the finite square well, right, the classically allowed region is inside the well. We saw in the last class that there the wave function is oscillatory, namely, right, it goes like e to the I kx or e to the minus I kx. Or if you want to think about sines and cosines, you can think about those. Now, why is this? We can see why by thinking about the time-independent Schrödinger equation. I can rewrite the TISE in the following way. But if I write it as the second derivative of my energy eigenfunction, right, equals minus E minus my potential energy over h bar squared times my wave function. We've got to be a little bit careful here, but if V is constant over some region, like it was for the finite square well, right? Right, then this is exactly the harmonic oscillator differential equation. Right, with k equals square root 2m E n minus my potential energy all over h bar. So there are some important physical takeaways from this, right? So the first takeaway is the behavior of the wave number, or equivalently the wavelength, inside my well, or in my allowed region, as I consider what happens to En minus V. So if I increase En minus V, so I can do that either here, right, by going to higher energy eigenvalues, or if I had a potential energy that was varying spatially, I can still sort of quasi think of this of k, even though it's not truly constant. I can think of essentially a changing wavelength, right? En minus V will increase as my V decreases, right? So let's sort of the takeaway, right? So as right, so either by my energy going up or my V decreasing, right? My K has to increase, which means that my wavelength, which is 2 pi over my K, 2 pi over K, goes down. And probably the easiest way to see that is from the finite square well, where as I increase from E1 to E2, notice that I now have a shorter wavelength within the well for this compared to my ground state. Also, it turns out, and this is something that is not obvious from what we did before, that as I increase En minus V, my amplitude goes down. This mainly comes into play when I have a potential energy that varies spatially. There's an argument I'll talk about in a bonus video that's a little involved but still a little hand wavy, that gives sort of a reason why this is plausible. There's also a heuristic, sort of wrong but sort of mnemonic device argument you can make. This you should take with a giant grain of salt, since the reasoning is not quite correct. It's one of those semi-classical arguments, so heuristic. Right. So having a larger En minus V right? Well, if I increase the energy compared to the difference between the total and the potential energy, what happens to the kinetic energy? It has to go up, right? So we increase K. Increased kinetic energy means that a particle is going faster, right? So particle faster. If the particle's moving faster, it spends less time in that location. Right? So you would expect that the probability of measuring the particle there to go down. So smaller probability, smaller amplitude. Okay. Now the reason why we need to take this with a giant grain of salt, right, is that in a stationary state, right, we know that, right, the probability density isn't actually changing, so it is at best fraught to think about. You know, we have a particle that's truly moving in any kind of classical sense, but this may help you remember this relationship, even though you should not take this reasoning in detail too seriously. So in the classically forbidden regions, right, where the energy is less than the potential energy, or for the case of the finite square well, outside the well, what we find is that the wave function, the energy eigenfunctions decay exponentially. We can see why by once again looking at the time-independent Schrödinger equation. And this time, right, what we get is d squared psi dx squared equals 2m, right, v of x minus e n psi n of x all over h bar squared, right? And so this goes like, right, kappa squared psi n of x with kappa kappa equaling root 2m v minus e over h bar. So again, the takeaway from this, and again, hopefully you saw this in the PhET, is that, you know, as I make, you know, v minus e smaller, so as my energy approaches the potential energy, so like as I go up here, right? So here if I increase Vx, rather if I increase my energy here, right, I decrease V minus E, right? And that is going to mean I'm going to decrease kappa. And if you think about what decreasing kappa means for an exponential decay, right? So for something that goes like this, right, the larger kappa is, the faster it decays away, right? And so if I decrease my kappa, that means that I'm going to decay away more slowly. And I couldn't really draw that super well here, but hopefully you saw that in the PhET yesterday, that as I go up in energy, my wave function penetrates further and further into my classically forbidden region because I have this slower, this more gradual exponential decay. So there are just a couple of other points that I'd like to make, and I've listed them in that handout for today. And in most of these we've seen in various guises already. So the fact that the energy eigenfunctions have to vanish where my potential energy is infinite, we saw that for the case of the infinite square well. There's also the idea that in general the ith excited state has I nodes. So let me explain what I mean by that. So, and the best case to think of here is the finite square well. So n equals 1 for the finite square well is the ground state, and it has no nodes. N equals 2 is the first excited state, and then it has one node, or one zero crossing, right at x equals 0. Okay? And similarly for the finite square well, psi 3 is the second excited state, and if you go back and look at the figures in Townsend or at the PhET, you'll find that that has 2 nodes. There's also the case that the wave function still has to be normalizable, and in practice what this means is that as you approach x approaches infinity or minus infinity, the wave function has to nicely decay away. As we talked about last time, in general we will also require the wave function and its derivative to be continuous. So you can't have any sort of funky cusps in your wave functions for energy eigenfunctions. And then the last thing that I want to mention is symmetry. I mean, this is sort of this is not so apparent. So namely if my potential energy is even, right, my energy eigenfunctions are either even or odd, right? So we concretely saw this for the finite square well. There's a sort of elegant way to prove this involving the parity operator that I think you'll talk about in physics 421, but I'm going to have to defer this. Then hopefully it's at least plausible based on what we've seen with the finite square well. So at this point, I have a bunch of exercises for you to work on. If we were together in person, at this point I would break you all up into groups, and we would probably have different groups work on different exercises, and then what's really fun would be to do a gallery walk at the end of the class. We can't quite do that here. I will use the Sakai forum to sort of open up a space for people to post any pictures of things they've tried sketching to maybe try to replicate some of this. This is worth thinking about, these exercises, so I'll leave you plenty of time to work on those. I'll close by showing you one example on my computer that ties together all of the principles that we talked about here, and then do go and try those exercises for yourself. So, this example, which is from Townsend, I think ties together quite nicely all the things that we talked about. So we have here, right, a well that has a step in the middle, and it's a finite well. So within the well, here we're told we're looking at E5, so this is going to be the fourth excited state, right? The energy is larger than the potential energy everywhere inside my well. There we see that the energy eigenfunction is in fact oscillatory. We also notice what I said about the wavelength and the amplitude. On the left half of the well, we have a lower V, which means that we have a larger difference between the total energy and V. And the result of that is that we have a shorter wavelength there and a smaller amplitude. The wavelength then increases on the right half of the well, where the total energy is closer to the potential energy. And we also see the amplitude of the wave function being larger there. Outside the well, right, we see that the wave function is in fact decaying in what looks like an exponential manner. And then the other thing I should point out here is the number of nodes. So we're told this is E sub 5, right? If we assume that E sub 1 is the ground state, E5 is the fourth excited state. So we should expect to see 4 zero crossings, and that's exactly what we have. So we have 2 in each half of the well. So this is a good example of the principles we talked about, and then the examples for the rest of today's class will give you further applications of those ideas. Hope you have fun.